From the initial learning session, you now have an idea about this random variable. Now, as we progress in this video, we are going to learn about the random variable. That means we'll have a quick recap on this random variable, and then we'll also see how we can describe this random variable with the help of various functions. So, to have a quick recap on this random variable is actually a function which maps every outcome in my sample space to a real number. So it maps every outcome in my sample space to a real number. For example, suppose if I have a sample space which contains about the experiment of tossing a coin or flipping a coin. So in my sample space, I'll have head and I'll also have tail. Okay, now this random variable is actually a function which maps, suppose if I call this random variable as a function r, and this function r maps every event that I've got in the sample space to a real number, which is like a probability number. So random variable, that is random variable function r, which helps me to describe the probability of occurrence of an event head, which is given by 1 by 2, that is 0.5, which is a real number. And it also helps me to map another outcome that I've got over here, that is tail, to another real number, that is 0.5. So this random variable is actually a function. Okay, it's actually a function. So the way that we would say is, so the probability where a random variable assuming the value of head, that is random variable r, assuming the value of head, that is given by 0.5. And in the same way, probability of random variable r assuming the value of tail. Okay, so in other words, we can also think of it as a function which helps me to map every outcome in my sample space to a real number. Now, depending on this random variable r, or this random variable function r, having the type of value, we can classify it as either a discrete random variable or continuous random variable. Now, if the random variable x can assume only finite or countable infinite set of values, then we call it as discrete random variable. If my random variable x, if it can take from an infinite set of values, then we call it as continuous random variable. Now, to give you an example, the examples for discrete random variables are credit rating, number of orders received in an e-commerce website, customer churn, fraud detection. So these are some of the examples for discrete random variable. And coming to continuous random variable, so market share of a company, percentage of attrition of employees, time to failure of an engineering system, time taken for an e-commerce company to complete the order. So these are some of the examples of continuous random variable. As you can clearly see, each of the values that we would get in this experiment, so each of the values that we can have in this overall sample space of this particular experiment, it can be in an infinite range and it belongs to continuous values. Hence, we call this random variable function as a continuous random variable function. Now, suppose if we are dealing with discrete random variables. Now, in such scenarios, we can describe using the probability mass function, that is PMF, and cumulative distribution function. These are the two functions that we will be using it to describe the discrete random variables. Here, specifically speaking, talking about PMF, that is probability mass function. So this probability mass function is the probability that a random variable x takes a specific value k. It's like the number of fraudulent transactions at an e-commerce company is 10. So in such scenarios, what is the probability of finding the number of fraudulent transactions at an e-commerce company equal to 10? That is, number of transactions equal to 10 is like finding the probability mass function. I can make use of this probability mass function and find the values of probability. Now let's suppose if I want to find the probability that a random variable x taking a value less than or equal to k. In other words, what is the probability that I would get the number of fraudulent transactions is less than or equal to 10. Okay, these less than or equal to 10. In order to calculate these kind of probabilities, we make use of CDF, that is cumulative distribution function. Okay, in case of discrete random variable, we've got PMF to find the probability that a random variable X taking a specific value K. And in case of CDF, it's a probability that a random variable X taking a value less than or equal to K. Okay, so this is about the discrete random variable. Next, we've got something called as continuous random variable. Now here, in order to describe the continuous random variable, we make use of PDF, that is probability density function, and CDF, that is cumulative distribution function. So PDF is the probability that a continuous random variable X taking a value in a very small neighborhood. Like, what is the probability that I'll be finding a home which is in the range of 100K and 125K. Now, in order to answer these kind of problems, we'll be making use of PDF. Suppose if I want to answer the problems like what is the price of house less than or equal to 100K, in such scenarios, I'll be making use of CDF, because CDF is the probability that a continuous random variable X taking a value less than or equal to K. So this is how we'll be describing the random variables depending on the type of the data it actually represents, and we'll be using the respective functions to describe the probability of such random variable. So as part of your learning journey in this video, you have learned about what exactly are this random variable, the core concept behind this discrete random variable, and the functions which will help us to describe such discrete random variable, and we have also learned about the continuous random variable. So as we progress in our next video, we are going to learn about the various data distributions. So I'll see you in the next video. In this video, we are going to learn about the probability distribution. So as we progress in this video, we will learn about the probability distribution functions that we have got for discrete random variables, and we'll also look into the probability distribution functions for continuous random variables. So let's start by looking at the probability distribution functions for discrete random variables. So the first function that I want to share right now, that is about for describing the discrete random variables, is binomial distribution function. So this is actually a discrete probability distribution. Now this is a scenario where my random variables, okay, my random variable has only two outcomes. It could be like a yes or no scenario, or true or false. Now the overall objective is to find the probability of getting X successes out of n trials. Okay. Now in this scenario, suppose if I have got the value of probability of success is mentioned as P, then from the rule of complement, I can say that the probability of failure is 1 minus P. Now the reason, because here this has only two outcomes. So which means there are only two events that are possible. So if I have got the probability of occurrence of an event, then the probability of occurrence of another event is complement of occurrence of an event 1. Okay, an example can be loan repayment default. So in such scenarios, we actually make use of this binomial distribution. And in order to express these kind of scenarios, okay, in order to describe the probability with the help of these scenarios, we actually make use of PMF and CDF. Okay, now apart from binomial distribution, we have got something called as geometric distribution. Now this geometric distribution occurs when you count the number of independent Bernoulli trials until the first success. Okay, where here my X is equal to number of trials Y until first success, number of trials Y until first success. In this scenario, the X will be distributed with geometric distribution. Okay, these are the two major discrete random variable distribution functions. Now let's take up an example. Here I've got an example problem. The example problem looks like this. We've got a company that's called as Fashion Trends Online, which is an e-commerce company and it sells women apparel. It is observed that 10% of their customers is going to return the items for many reasons. It could be due to size, color, and material mismatch. Now, on a specific day, 20 customers have actually purchased from the website. Now, as a data scientist, you have to solve the problem. The problem is, what is the probability that the exact 5 customers is going to return the item? What is the probability that the maximum of 5 customers will return the item? What is the probability that more than 5 customers is going to return the items purchased by them, and the average number of customers who are likely to return the items, and the variance and the standard deviation of the number of returns. So let's take up the first problem here. Probability that the exactly 5 customers is going to return the item. So this is a scenario, okay, where it's a discrete random variable. Now in this scenario, I'm interested in finding what is the probability that exactly 5 customers is going to return the item. Now in that scenario, I can make use of PMF, that is probability mass function, and solve the same. And here maximum of 5, so which is like CDF, and the third one is it's the complement of second one, that is like 1 minus CDF, and the last one is an average one. So this is the given data. So let's go ahead and implement this in a hands-on manner. So what I'm going to do right now is, okay, we'll go directly to our Google Colab and let's start coding over there. I'm now in my Google Colab. So from a given data set, okay, so let me just show you how does the data would look like. That is our example problem. So this is the example problem that we have got. So here in this scenario, let's take up this example right here. So I'll just take this screenshot so that we have it as a reference in our hands-on. Okay, I'll paste the screenshot over here so that even you will have it as a reference. Okay, this is a example problem set. Okay, now here from the given data set, okay, this is the given data for us. Now what we are going to do right now is, in order to find the values of PMF and CDF, okay, so this PMF and CDF functions are available inside this scipy.stats module. So I'll import it in this way from scipy.stats. Okay, I'll dot binomial. I will import my PMF function as well as the CDF function. So the first question over here, okay, the first question over here says, what is the probability that exactly 5 customers is going to return the item out of 20 customers who have actually purchased on that specific day? Okay, so this is the given data. All right, so I'll do it in this way from SciPy. I'll just import stats. So in order to answer the first question, I have to find the value of PMF. So stats.binom.pmf, and inside the parenthesis, we have to mention the value of K, that is the quantities, the exactly 5 customers. So the K is actually 5. And the second value is actually nothing but the total number of samples that I've got, that is 20. And the third value is actually the probability. It is observed that 10% of the customers is going to return. So probability is given by 0.1, that is K comma number of samples comma probability. Okay, so this is the value that for this probability mass function, and in this scenario the value of probability is given by 0.031. Okay, so it means there's a 3.19% of chance that exactly 5 customers is going to return the items on a specific day. Okay, next, moving on. Okay, let's go ahead and solve the second problem. The second problem or the second question here says probability that the maximum of 5 customers. So this is like the scenario of CDF, which means in this scenario I would say stats dot binomial distribution dot CDF. Okay, 5 comma 20 comma 0.1. So this is a scenario where 5 or 5 or less than 5. So the probability that 5 or less than 5 people are going to return on that specific day is 98.87%. Now the third question, it's like the complement of the first one, that is the second one. So here it is 1 minus stats.binomial distribution.cdf of 5 comma 20 comma 0.1. In this scenario, so this says that there is 1.1 percentage chance that more than 5 customers are going to return on that day. Okay, that is how we interpret the answer. And the last one is getting the value of average as well as the variance. Okay, so in order to get the same, we can get it by specifying the values inside the stats method. So I'm going to say average comma variance is equal to stats dot binoms dot stats. 20 is the number of samples and probability is 0.1. And if I display the value of average is actually 2. Okay, because 10% of 20 is obviously 2. That's the average value. And if I want to display the variance, the variance is actually 1.8. So the average number of customers who are going to return the items is 2 and the variance is actually given by 1.8. And here if I want to get the standard deviation is nothing but square root of 1.8. So this will be my standard deviation, which is 1.34. All right, team. So this is how we can make use of PMF and CDF and answer the question. I hope you can correlate with the theoretical explanation with this hands-on problem. Okay, now coming back to our slide. So we have now solved this problem about what is the probability that maximum 5 customers is going to return on that day or more than 5 customers and the average number of customers. Moving on. Let's look at the probability distribution functions of continuous random variable. So here under the continuous random variable, we've got uniform distribution. Now uniform distribution is a probability distribution which has a constant value in each interval. You can clearly observe in this given slide. So we've got something like a rectangle shape. Hence this is also known as rectangular distribution as well. And we've got something called as exponential distribution. So this exponential distribution provides a way to find the probabilities in time for a process. Traditionally, this exponential distribution is used for modeling time to failure of an electronic component. And this exponential distribution represents a process in which events occur continuously and independently at a constant average rate. So this is about the exponential distribution. Apart from this, we've got something called as normal distribution, and this is one of the most important probability distribution in the field of statistics. And most of the machine learning algorithm assumes that the data follows this normal distribution. And the best part is this is one of the distribution which fits several natural phenomena. An example can be measurement error, heights, IQ error, blood pressure. All these natural phenomena that we observe in our real life, it follows the normal distribution. And here, when we are talking about this normal distribution, so we'll be describing the normal distribution with the help of standard deviation and mean. So this normal distribution, it depends on two factors, that is mean and standard deviation. So this value of mean determines the center of the graph, that is the location of the center of the graph, and the standard deviation determines the height of the graph. Okay, so this is about the normal distribution. So as part of your learning journey in this video, you have looked into the various probability distribution functions of discrete random variable as well as the continuous random variable. Now, as we progress in the next video, we are going to learn and perform an hands-on activity of generation of random numbers. So, I'll see you in the next video. In this video, we are going to generate the random numbers and visualize the various distribution functions that we have got. So this will be an hands-on video where we are going to generate the random numbers. So let's start coding and let's go directly to the Google Colab and I'll start coding the same. So I'll switch to my Google Colab screen. So first thing is, let's generate some random numbers. So before that, I'm going to import the necessary libraries. I'll import matplotlib library. And I'll also import the Seaborn library as well. Okay, so let's start by generating the values which are belonging to the discrete random variable. So first thing that we are going to do is we are going to generate the random numbers which is following Bernoulli distribution. So let's go ahead and do that. In order to generate the random numbers using which is following this Bernoulli distribution, so we've got a function from scipy.stats. So from scipy.stats, I'll import Bernoulli. Okay, now I'm going to generate my Bernoulli data. I'll say data is equal to Bernoulli.rvs. Okay, this is a function and I'll specify my size. I'll mention my size as 10,000 and I'll mention my value. Okay, I'll mention the value as p is equal to 0.4. Okay, so this is how I'll be generating the data with the value of p is equal to 0.4 and I'll mentioning my size. Now once I've generated the data, I'm going to say sns.distplot and I'm going to mention my data, and here plt.xlabel I'll mention as Bernoulli and plt.ylabel frequency, and finally plt.show. So if I execute this, this is going to create me a Bernoulli distribution. I mean, this has generated the random data points which follows the Bernoulli distribution. Okay, since we have mentioned the probability as 0.4 and 0.4, we observe the same thing over here. We've got 60% of data is having the value as 0 and 40% of data is having the value as 1. Okay, so in this way we can generate the data which follows the Bernoulli distribution. Now let's go ahead and generate the numbers which follows the binomial distribution. Let's go ahead and generate the data which follows this binomial distribution. So in order to generate the same, so what I'm going to do is I'll just copy this code and I'll paste it over here. So instead of Bernoulli, I'm going to import this binomial and I'll say binom.rvs. It is binomial, and here I'll mention my number. So let's say I'll mention my n is equal to 10. Okay, this is how I'll be specifying the value of n, and along with that, this time I'll set the value of p is equal to 0.5. I'll keep the value of size as 10,000. So when I execute this, this is going to generate and create the visualization which is the random numbers which follows the binomial distribution. Okay, even this binomial distribution comes under the discrete random variable. Next, I'm going to generate the numbers which follows the geometric distribution. Now this is an interesting one. So import GEOM. I'll specify p is equal to 0.5 and I'll keep the value of size as 10,000. And instead of like binomial, I'll say geometric. So this is going to create me a visualization which follows the geometric distribution. Okay, now let's go ahead and generate the data which follows the continuous random variable. I mean, we'll generate some random data which describes the continuous random variable. So first thing that I'm going to do is I'm going to generate the continuous random variable which follows the uniform distribution. Okay, so this is about uniform distribution. So I'm going to specify my n as 1000, that is the number of data points that I want to generate. I'll mention my a as 0 and b as 10. Okay, for my uniform data, okay, I'll just directly say it as data and I'll say in order to generate the data which follows the uniform distribution, from scipy dot stats, I'll import uniform. So uniform, inside the parenthesis, I'll mention the size as n, okay, and loc as a, scale is equal to b. Okay, sns.displot, we are going to specify the data and I'm going to mention my number of bins as 100. Okay, and here plt.xlabel, so this is actually my uniform data, uniform distribution, and for the y label it's actually the frequency and will display the plot. So if I execute the same, this has generated the data. See, this has generated the data for me. So which has got the a as 0, okay, and we have mentioned the b as 10. So this follows the uniform distribution. Okay, this follows the uniform distribution. Now let's go ahead and generate the data which follows the exponential distribution. So let's see how does this exponential distribution data would look like. I'll say exponentiation, that is expon dot rvs. Okay, and here this time I'm going to specify my scale. Let's say I'll mention the scale as 1. Okay, I'll keep the log as 0 only and I'm going to generate the 100 data points. So exponential, and here when it comes to x label, I'll say exponential. So if I execute this, this is going to generate the data which follows the exponential distribution. See, now let's go ahead and generate the data which follows the normal distribution. So from scipy.stats, norm, and I'm going to say norm.rvs. Here I'm going to specify my number of data points. This time I'm going to generate some more number of data points, log as 0 and scale as 1. Okay, now let's go ahead and create the plot. So this is actually my normal. Okay, so if I execute this, this has generated the data which follows the normal distribution, which has got the mean as 0. Okay, and it also has the standard deviation as 1. So as part of your learning journey in this video, what you have learned is you have learned about the various functions that are available inside this scipy library to generate the data points which follows a specific distribution. You can use this to check how does the real data distribution would look like and compare it with your existing data set whenever you are doing the analysis. Okay team, so with this we come to the end of this video. In the upcoming video we are going to learn about the central limit theorem. So I'll see you in the next video. In this video we are going to learn about the central limit theorem. So as we proceed, we'll learn about the central limit theorem and we'll take up a hands-on approach to learn and validate this central limit theorem. So let's start by understanding what exactly is the central limit theorem. See, the central limit theorem states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample that I've got is large enough. So what it means is, suppose if I've got a very large data and if I select multiple samples, then these means of this individual samples follows the normal distribution, and that is the overall idea behind the central limit theorem. You'll get a better idea if we implement this in a hands-on manner. So let's do one thing. Let's implement the central limit theorem in a hands-on manner so that you get the clear understanding as what it means by central limit theorem and how it is actually useful for us. So I'll go to my Google Colab. So here I'm now in my Google Colab. I'll start by importing the necessary libraries. I'll import my NumPy library. And along with that, I'll also import the matplotlib library, matplotlib.pyplot as plt. Now I'm going to generate some sample. Okay, I'll generate my number of samples as num is equal to 1, 10, 50 and 100. Okay, and I'm going to calculate the means. So this is like the Python list. Okay, so this Python list will actually contain the sample means. Okay, now what I'll do is I'm going to generate the various random numbers between -50 to +50. So I'll generate 1, 10, 30, 100 random numbers from -50 to +50. Okay, and what I'll do is I'll take the mean and I'm going to append it to my means list. So in order to do the same, I'm going to say for I'm going to say I in num. Okay, this is a for loop that I'm going to create. Now inside this for loop, I'm going to say np.random.seed. I'll set the seed as 0. Okay, and I'll say my x is equal to np.mean. Okay, this is a mean of np.random.randint, and I'll be generating the random integers between -50 to +50, and the number of digits is actually I'll set as I. Okay, and I'll do it for I'll say underscore in range 1000, which means I'm going to generate the random numbers between -50 to +50. Okay, I'll generate the random numbers between -50 to +50, and this I is the number over here. Okay, and once I generate it, the value, I'll calculate the mean, and at the end I'm going to append this value of x back into my mean. Okay, next I'm going to say my k is equal to 0. Okay, I'm going to create a plot, plt dot subplots, and 2 comma 2 comma, I'll mention my fixed size as 9 comma 9. Okay, next I'm going to say for I in range 0 comma 2. Okay, next for j in range It's the same. I'll mention it as 0, 2. Now inside this, I'm going to create the histogram. Okay, I'll create the histogram. I'm going to say AX, okay, I comma J hist, and I'll get the means, okay, means of K, and I'll say 10 as the bins, and I'm going to say density is equal to true. Next, I'm going to set the title. So AX I comma J. Okay, I'm going to say title label is equal to num K. Now finally, I'm going to set as plt.show. Now if I execute this, this will help me to create a visualization. So here, this is how my overall visualization would look like. Okay, so here it looks like it has considered only one sample. Let me just validate over here. So here in this scenario, okay, so there was one missing, that is K is equal to K plus 1. So this was actually missing. Once I added this, this is how the overall visualization would look like. Now, as you can clearly see from the given data set, as we keep on increasing the sample size from 1 to 10, that is still 100, as I keep on increasing the size of my sample size, the histogram tends to take the shape of the normal distribution. Okay, so the term large is actually a relative one. Roughly, the abnormal basic distribution. The larger n must be the formal approximation to work well for a given data. So just think like this, team. Okay, so we need to have a large data set. Okay, so the overall idea is, as I have more number of sample size, and as I start generating the random data, and we can clearly observe its respective mean follows the normal distribution. Okay, so this is how we can make use of central limit theorem and prove this central limit theorem. So in this video, you have learned about the central limit theorem, and you have validated the central limit theorem in an hands-on manner. As we proceed in the next video, we are going to learn about the applications of probability distributions. So I'll see you in the next video. In this video, let's look at some of the important applications of probability distribution. So as we proceed, we'll look into the discrete probability distribution, and we'll have a quick recap on the continuous probability distribution, and then we'll look into those applications. So let's get started. Now, under this discrete statistical distribution, we've got binomial distribution, multinomial distribution, geometric distribution, and Poisson distribution. So we generally make use of this binomial distribution to answer the questions like, what is the probability of 7 or more heads in 10 tosses of a fair coin? So if you remember, we have taken a similar example in our fashion data as well, isn't it? So that was actually a binomial distribution. And we make use of the multinomial distribution. And to give you an example, let's say we've got 4 companies. They're actually bidding for each of the 3 contracts with specified success probabilities. Then to find the probability that a single company will receive all the orders, in such scenarios, we make use of this multinomial distribution. Coming to geometric distribution, given a lot of 21 good units and 4 defectives, what is the probability that a sample of 5 will yield not more than 1 defective? Now, in order to answer such example problems, we make use of this geometric distribution, because if you remember the definition, that is the overall idea behind this geometric distribution, that is the number of failure till first success. Okay, and Poisson distribution, it is used to represent the distribution of number of defects in piece of material, customer arrivals, insurance claims, and so on. So this is about the various discrete statistical distribution and its usage. And coming to continuous statistical distribution, Under this continuous statistical distribution, we've got normal distribution and uniform distribution. So when it comes to normal distribution, so this normal distribution is what we observe in real time, which is in distribution of physical measurements on living organisms, average temperatures, and so on. And coming to uniform distribution, this is used to generate the random values. Next, let's look at the applications of probability distribution. Well, probability distribution is used in forecasting, that is predicting the future sales level as likely or worst case or best case sales scenarios. And in the field of customer service, that is time analysis of customer requests and types of requests. In such scenarios, we make use of probability distribution. And coming to investment, so risk analysis can actually be done using probability distribution, which will help the business to plan their investment. And even this probability distribution is used in product design as well, where we'll be designing the product using the model that is based on probabilities of failure or breakdown of different parts. So these are some of the important applications of probability distribution. So as part of your learning journey, so you have understood about in which scenario what kind of distribution can be used and the various applications of probability distribution. So as we proceed in our learning journey, we'll be learning in the next video as how we can convert the data into a normal distribution. So we'll look at it in an hands-on manner. So I'll see you in the next video.
In this video, we are going to learn how we can convert the data to normal distribution. Now this session is a hands-on session where we'll be performing in an hands-on manner so that we'll understand how we can convert the data into a normal distribution whenever we are given with the continuous data. So let's get started, and let's start by starting our initial notebook, that is with the Google Colab. So I'm now in my Google Colab. Now what I'll do is I'll start by loading the necessary data set. Okay, so that is the first thing that I'll be doing. So when I execute this cell, so this is going to download the necessary data set from the Google, from my personal Google Drive account. Okay, now the reason that we are learning this activity, because in the scenario of machine learning and deep learning, most of the models like the linear regression model, logistic regression model, and the artificial neural network assumes that the features are normally distributed, and it actually performs better whenever we have got the continuous features which is actually in normally distributed format. Okay, so in such scenarios, yes, in such scenarios, it's very important that we bring the data in the format of normal distribution. So as we proceed in this video, let's see what are the various ways that we can convert the data which is not in normal distribution, and we can convert it into a normal distribution format. So first we'll understand how we can check whether the data follows the normal distribution, and then we'll look into the various methods of converting the data which follows the normal distribution. So here, first thing that we can do is we can start by checking the skewness of the data set. So we'll start by checking the skewness with the data set. So in order to check for skewness, first thing that I'm going to do is I'm going to import my necessary libraries. So I'll import my pandas library, I'll import my numpy library, and I'll also import the matplotlib library. Okay, once the libraries have been imported, I'll start by loading the data set. So the data set that I'm loading right now, it's called as carprice.csv file. So I'm going to say cp is equal to pd.read_csv, and I'll mention the file name, that is carprice.csv, and then cp.head. This will display first few entries of this data frame. Okay, so this is how our data frame look like. Now what I'm going to do right now is Let's check by understanding the skewness that we have got with the data set. If I say cp.skew and if I execute this cell, okay, so here we've got the values, that is, this values represents the skewness in the data set. So from this result, we can check whether a column that we have in a data set, whether it follows normal distribution or not. Now, whenever I've got the columns with the skewness, so I'll just write down the important things over here in the notebook so that you can remember whenever you are revising these topics. So whenever I've got the skewness which is greater than 1, so let's look at the columns that is greater than 1. So we've got the columns like wheelbase, and we have got horsepower, compression ratio. So these are the columns where the skewness is greater than 1. So I can say these are the columns which are highly positively skewed. These are the columns which are positively skewed. And the variables. So if I've got the variables with skewness value less than -1, okay, so let's see if we have any columns which has the skewness less than -1. So we don't see any columns which are less than -1. So if I have got any values which are less than -1, then they are highly negatively skewed. They will be highly negatively skewed variables in a data set. And if I can have any skewness, okay, if I have any skewness values, if it is between 1 to 0.5. So if I have any skewness values which is between 0.5 to +1, then I can say these are the columns which are moderately positively skewed. So in this scenario, I can say that the columns like car width, curb weight, so these are some of the example columns where I can clearly observe they are moderately positively skewed data. Similarly, if I have the skewness values which are between -0.5 to -1, okay, if I have got the values in the range of this -0.5 to -1, okay, -0.5 to -1, that then those are the columns, they are moderately negatively skewed. Okay, and if I have any data, okay, if I have any data which is in the range of -0.5 to +0.5, we can say those are the columns that follows the normal distribution. So columns in the range of -0.5 to 0.5, they are the ones which are normally distributed columns. So this is one way of checking whether the distribution of my data set follows normal distribution or not. So just get the skewness of each and every column. On the basis of skewness values, we can check whether the given columns are normally distributed or not. So from this analysis, I can say that the columns such as symboling, car height, and bore ration, that is bore ratio, and we've got peak RPM, highway MPG. So these are the columns where we can clearly observe it actually follows the normal distribution. Okay, so getting the skewness is one way, okay, of checking the normality in a given data set. The other method that we can do is we can create a histogram chart. Okay, histogram chart also helps me to understand the overall distribution in a given data set. Now what I'm going to do is I'm going to select a column. Let's say we'll select the column of horsepower. Okay, I'm going to say CP horsepower dot hist. Okay, next I'm going to say title. The title I'll add is horsepower So if we create a histogram chart, so this will let us know whether this column follows the normal distribution or not. So from this given distribution, with the help of this histogram chart, we can clearly observe this is the column which is highly positive skewed. So this column is highly positive skewed. So the column that I've used is horsepower, and you can also check as well. See, if you look into the skewness value for the horsepower, it is more than 1. Okay, so this is another way to check whether a column follows the normal distribution or not. Now let's pick up the another column. So this time I'm going to select the column of stroke, which is moderately negatively skewed. So let's look at the representation of this column when we create a histogram chart. So the column name is stroke. So here we can clearly observe it is moderately negatively skewed and it does not follow the normal distribution. Okay, and let's pick up one more column. This time I'm going to create the histogram chart for the column of highway MPG, which follows the normal distribution. So highway MPG. So if I execute this, so this clearly follows the normal distribution because the data distribution is symmetric. Okay, so this is another way of checking whether the given data follows the normal distribution or not. So first method is with skewness, the second method is with histogram method. Okay, so these are the two methods that we have seen till now. Now apart from that, we can also check the distribution of the plot using the KDE plot. Using the KDE plot, we can also check the distribution. So I'm going to import my CMON library and I'll say sns.kde plot, and I'm going to say this time I'm going to create the plot for compression ratio. Now if I execute this, see, this is the overall output that I've got for the compression ratio. Okay, now in the same way I'll create a KDE plot for price column. So here, okay, this is the overall visualization that I've got for price column. So from this, both the plots, I can clearly observe that these two variables are highly positively skewed column and they are not following the normal distribution. Okay, and the other way to check for normality in a given distribution is with the help of QQ plot. Now a QQ plot is actually a scatter plot, and this is created by plotting two sets of quantile against one another. If both the sets of quantile come from the same distribution, then in such scenarios we should see the points forming roughly a straight line. That is the overall idea about this QQ plot. Now in order to create this QQ plot, I'll start by importing the necessary libraries. So I'm going to say import scipy.stats as stats. Okay, and I'm also going to import the PyLab. Next, I'm going to create a plot. So in order to create the plot, so stats.prob plot, and inside the parenthesis I'll just mention the column of price column, and here we will mention the plot is equal to PyLab. Okay, so here I'll execute this. This will help me to create a plot. Okay, so this has created me a QQ plot. So from our plot earlier, we have clearly observed that this price variable is actually a highly positively skewed column. So when we created this QQ plot, See, we are able to observe the same. The x-axis in my current plot, so it actually has the theoretical quantile values, and y-axis has the price values. So from this given plot, we can analyze that the data points of the price feature, they are not actually falling on this straight line. So this would imply that this given data does not follow the normal distribution. Okay, now next what I'm going to do right now is I'm going to make use of the another column, that is CTMPG column. So I'll say CTMPG. Okay, and the reason that I'm using this CTMPG, because here this CTMPG is a column which follows the normal distribution, as we have observed earlier with the help of skewness values. Now if I execute this, so this clearly we can observe that majority of data points falls on the straight line. Hence, we can say that this is a plot, or this is a column which follows the normal distribution. Okay, so till now we have seen the various methods to check for normality for a given data. But the thing is, so how can we get the data in the normal distribution? Suppose if the given data is not present in normal distribution to begin with. So that is where the transformation comes into picture. Okay, so what I'm going to do right now is I'm going to create a Python function which will take the data and the feature name, and it is going to return the KDE plot as well as the QQ plot for that feature. So this will help us in creation of the visualization and doing the analysis an easier one. Okay, so this is the plot that we are going to create. So this is a function, okay, which takes data and the feature, and I'm going to create the KDE plot in this subplot region. Okay, now once this is done, the next thing that I'm going to do is, so we'll start by performing the activity of transformation. See, whenever we are converting the data, okay, in order to convert the data from general distribution to normal distribution, the most commonly used transformation are log transformation, square root transformation, okay, and we can also make use of reciprocal transformation and exponential transformation, and we also have something called as Box-Cox transformation. So these are the various methods that we can actually use it to convert the data into the normal distribution. Okay, now to get started, I'll start by applying the logarithmic transformation on a given data set. Okay, so let's do one thing. Let's select a column. Now I'm going to select the column of the price column, and let's see whether it follows the normality or not. And from there, we'll apply the transformation. I'll say normality, and my data set is car prices, and the column that I want to analyze is price column. Now if I execute this, this is creating me two plots. One plot is a KDE plot, and the other plot that we have got is actually a QQ plot. So clearly this column or this variable does not follow the normal distribution. Now let's start by performing the log transformation. So this time, in order to perform this log transformation, I'm going to say log price is equal to np.log here CP price. Okay, now once this is done, this time I'm going to create the plot. So normality, and my data frame is CP, and my feature is log underscore price. So once I execute this cell, so this time clearly we can observe that the distribution has changed slightly, and now instead of having the completely skewed, now the data set is moderately skewed, and we can clearly observe we've got more data points falling on the straight line in the QQ plot. So this is the importance of log transformation. Okay, so this is how we can clearly observe having the log transformation. It also helps us in reducing the skewness that we have got in the data set. And the other transformation method that we can apply right now is the reciprocal transformation. Okay, it's the reciprocal transformation. So the way that we apply this reciprocal transformation is, so I'll create a new column, price reciprocal, and this is equal to 1 divided by CP price. Okay, next let's check for normality. So CP and the column name is price reciprocal. So now also we can clearly observe most of the data points are on the straight line. We can clearly observe. So the reciprocal transformation has kind of converted the feature into the normal distribution. And we can clearly observe this reciprocal transformation has also have got a better effect when it comes to conversion compared to the log transformation method that we have seen earlier. Okay, and the other method that we have got is the square root transformation. Now when we talk about the square root transformation, this transformation is going to take the square root of the given feature. So in this scenario, the square root of the price column. So I'm going to say CP square root price is equal to NP dot square root of CP price. Okay, now once this is done, we'll create a plot, normality, and inside the parenthesis I'll specify my data and the feature name. So this is going to create a plot, and it has kind of removed the skewness in the data set. Okay, so it has reduced the skewness and it is taking my data towards the normal distribution. Okay, so moving on, the other transformation method that I have explained earlier is the exponential transformation method. Now in this exponential transformation method, we are going to take the exponential value. Okay, we will take the exponential value of the price variable in this example. So I'll say CP exponential price is equal to, I'm going to say CP price and to the power of 1 divided by 1.2. Okay, this will take the exponential this will perform the exponential transformation. Now I'm going to create a plot. So by sending in the data, that is CP, and the feature, that is exponential price. Now if I execute this, so this has performed the exponential transformation. Okay, and the another way that we can actually perform this activity of conversion of data from skewed distribution to normal distribution is with the help of Box-Cox transformation. So let's go ahead and perform this Box-Cox transformation. Now in order to perform this Box-Cox transformation, I'm going to write it like this. I'll say CP Box-Cox price comma parameters is equal to stats dot Box-Cox, and inside the parenthesis I just have to send in the column, that is my price column. And now I'm just going to create a plot. So normality, and the column name is boxcox price. And now by performing the boxcox transformation, even in this scenario, we can clearly observe that. So this technique, that is a boxcox transformation technique, have actually given us the good result, and they have actually converted the data to follow the normal distribution. And we observe the same in the QQ plot as well. So from all these given transformations that we have done till now for the column of price, I can say that the box cost transformation and the reciprocal transformation, they actually perform the best on this given column, and they will perform best in converting this column to the normal distribution one. Okay, so in this way we can check for normality in a given data set, and also we can convert the data which does not follow the normal distribution into a distribution that is normal distribution 1 by applying the various transformation techniques. So with this, we come to the end of this video. As we proceed in our learning journey, in the next video, we'll also take some of the other hands-on examples of probability and we'll implement it in a hands-on manner so that we can recap and revisit the important topics of probability that we have learned till now. So I'll see you in the next video. In this video, let's take up some of the examples of probability and compute the values of the probability for the set of given events. So let's get started, and let's start by going to the Google Colab and let's start coding. Okay, it's a very simple problem. So it's very similar to the concepts that you have learned till now. So I'm now in my Google Colab. So the first problem that we have got is about the lottery, that is the spin the wheel example. Okay, so there is a game that's called as spin the wheel. Now you are going to win the game. Yes, you are going to win the game if you get an orange. So if when the wheel comes to the stop, once the spin is complete, if the orange color is the one that you get, then it means you have actually won the game or you have actually won the lottery. Now in that scenario, I want you to tell me what is the probability of winning the game if the spin wheel looks something like this. So if you do a single spin, what is the probability that you are going to win the game? So obviously, let's count the sample spaces that we have got right here. So in my sample space, there are actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are actually 12 events that are possible in my sample space. And the event which I'm interested, so that is the orange strip. So there are actually 3 orange strip that I've got. So orange is the one which will help me to win the game. So if I want to calculate the probability, see, calculation of probability is nothing but I would say that print probability of winning the lottery is, and I'll just say E by S, that is number of events by sample space. So the probability of winning the game is 0.25. So it will be 0.25, that is 3 by 12, 1 by 4, which is nothing but 0.25. Okay, so this is the answer for this first problem statement. Now the next example that I've got right now, it's the food delivery example. Okay, so let's say the business, they want to analyze the orders that were received from the customer on a specific day. Okay, so on a specific day, these are the list of like this is the complete list of items that they have ordered, and the orders received on that day, like it actually describes the individual cuisines. On only vegetarian there were actually 10, and only international cuisine is 25, and North Indian cuisine was ordered by 10 people, South Indian cuisine was ordered by 20 people, desserts were ordered by 10 people. Now let's come up and let's find the probability of ordering a specific type of dish. Now, if I want to calculate, okay, probability of ordering only international cuisine. Now, if I want to answer this, then it's very simple. Probability is given by E by S. So my sample space is nothing but it's the sum of all the events, that is 10 plus 25 plus 10 plus 20 plus 10. Okay, and my event which I'm interested in, it is 25. So probability is given by E by S. So if I display this P, that is the probability score. So the probability of ordering the international cuisine on a given day is 33%. Okay, so this is how I can find the value of probability. Similarly, if I ask you to find the probability of ordering a dessert, okay, probability of ordering a dessert, it's the same thing, only difference is my E is actually 10. So the probability of ordering a dessert is 13.33%. Okay. Now, these are all the examples for straightforward operation of probability. Now let's go ahead and let's make use of the rules of probability. Now I've got a bakery data. Okay, I've got a bakery data, and this bakery data looks like this. Okay, so this bakery has, let's say, it has the chocolate cupcake. So I'll mention it as, let's say, 10. Okay, and it has got the strawberry cupcake. So it's 5. Okay, and this bakery has, let's say, chocolate donuts. It has got 8, and it has got some Black Forest ice cream, or let's say Black Forest cake. Okay, I'll mention it as 10. And I have got some strawberry donut, and there are actually 4. Okay, these are the various dessert items that are available in a bakery. Now what I want to do is I want to find what is the probability of getting, okay, if I'm selecting an item in a random out of all the items that are present right here, I want to check what is the probability that I'll be selecting a Black Forest cake. Okay, I want to find the probability of getting the Black Forest cake. So in such scenarios, obviously my E is given by 10, the event that I'm interested, and the total sample space is given by 10 plus 5 plus 8 plus 10 plus 4. Okay, so probability is given by E by S, that is, in this example, the probability of getting the Black Forest cake is 0.270. Okay, this is the probability of getting the Black Forest cake. Now, let's say, okay, I want to do one thing. Let's say in this scenario, I want to find what is the probability that if I pick any random item that belongs to a strawberry flavor. Okay, probability that I will pick an item belongs to strawberry flavor. See here in this example, okay, there are 2 items which belongs to strawberry flavor. One is strawberry donut and the another one is strawberry cupcake. In other words, I'm trying to find the probability of getting the strawberry cupcake or probability of getting the strawberry donuts. Now that is what I'm trying to do right now. Probability of getting either cupcakes or donuts. So in such scenarios, we can make use of addition rule of probability. Okay, it's an additional rule of probability. So for the given data set, I can say that, so if I want to if I want to find the solution, it's like probability of getting these strawberry cupcakes plus probability of finding the strawberry donuts. Okay, this is the addition rule of probability. So I can do the same thing. Now this time if I want to find the values of probability, so strawberry cupcakes is actually 5 plus strawberry donuts is 4 divided by the sample space, that is yes. So the probability is given by 0.2432. Okay, 0.2432. Alright team, so with this we come to the end of this video. So in this video we have looked into a very simple examples of probability to help you recap on the basics of probability. So as we progress in the next video, we are going to look into some more hands-on examples of probability. So I'll see you in the next video. Hey everyone, and welcome back to your learning journey. And in this video we'll take up a project which is a hands-on project on cars data set. So let's get started and let's start coding and let's solve the problems related to probability using the cars data set. I'll begin by creating a new notebook and then we'll start by loading the necessary data set. Okay, so this is how I'll be loading my necessary data set. So this will ensure that the data set that we would require gets loaded automatically from the Google Drive account. So section 3, cars data set project 9. Okay, now here for a given data, okay, we'll start by analyzing this given data set. So the data set that we have been given, it's called as cars data set. Okay, now if I want to give you a background, let's say there is an automobile vendor and he wants to analyze the cars that has been sold in the past month so that he can improve his sales. Now the first thing that the vendor is currently interested in doing is he wants to do the analysis on the basis of car body type, and he wants to understand which body type have been sold in a maximum among all the cars that he has actually sold. So let's start by loading this data as a data frame and display first few entries of this data set. So import pandas as PD. I'll import NumPy library as well. df is equal to pd dot read underscore csv cars dot csv. And if I display first few entries of this data frame, so this will display the first few entries of the data frame. So we've got various columns that we have got over here, and we have got the car name describes the name of the company, fuel type, which tells me what is the fuel type, whether it is gas or diesel. It is obviously a categorical data. Aspiration, which is also a categorical data, that is aspiration used in the car. Door number, which is nothing but the number of doors in the car. Car body, what is the body of the car, and the type of the wheel drive, whether it is forward wheel drive or rear wheel drive or four wheel drive, and then engine location. So these are all the categorical variables, and we also have the numerical variables like wheelbase, car length, car width, car height. So these are some of the numerical variables that we have got in this given data set. Now there are actually total 24 columns. So what we will be doing is we'll start by analyzing which car body type has been sold maximum. Okay, in order to do that, what I'm going to do is I'm going to group by on the car body type, and I'll create the count to get to know as how many number of entries that we have got. Or we'll do one thing. The best part is I'm going to say df and car body value underscore counts. So this will tell me as how many number of entries that are present for each body type. So for sedan we've got 96, hatchback 70, wagon it is 25, and then hardtop is it 8, and then convertible it is 6. Now what I'm going to do is I'll be calculating the probability. What is the probability
that if I pick any random car, okay, what is the probability that it belongs to the sedan one? Okay, what is the probability that the given entry belongs to the sedan one? So I'll just say E is equal to 96 because that's the one for sedan, and my sample space has these entries. I'll just perform this summation. Then probability is equal to E by S, and the probability is given by 0.468. So this is the value of a probability. Okay, so here what I have done is I've just found the probability of occurrence of an event, which is nothing but a marginal probability. Okay, now let's go ahead and solve the other kind of problem. Let's take an example of joint probability. Now here, so we have found that sedan is the one, okay, sedan is the one which is highest sold. Now what I'm interested is I want to get, okay, I want to check as what is the probability of getting the sedan with gas type, like with the fuel type as gas. So in order to get that analysis, I'm going to create a cross tab, okay, and I'll create the cross tabulation between my car body, and I'll also get the fuel type as well, and I'll say margins is equal to true. So this time I have got the what we say, the split among the fuel type as well. Now if I want to find probability of finding the sedan, and the gas type is 81 divided by total sample space that I've got. So this time my event space is 81, so probability is given by E by S. So the probability of finding the sedan car with the gas fuel type is 0.39. Okay, so this is how we can solve the problems related to joint probability. And now if I want to extend the same to the conditional probability, so I want to extend the same to the conditional probability. So here it says, let's take up a scenario. Okay, so what is the probability? Okay, what is the probability? The question goes like this: what is the probability that a car is sedan given it is a, yes, given it is a gas fuel type? So this is a scenario, okay, this is a scenario where I want to find the probability of occurrence of event A given event B, okay, given event B, which is nothing but probability of A union B divided by probability of B. Now in this example, the probability that the given car is sedan, so the A is nothing but the sedan, probability of getting a sedan, given that it is a gas fuel type, that is A and B occurring together. Now in this scenario, so probability of A union B is given by the sedan and the gas fuel type, that is 81, and probability of B is nothing but, that is probability of having the gas fuel type. So the number of entries with gas fuel type is actually 185. Okay, so now this time probability of A given B, okay, A given B is given by, so it is 81 divided by 185. So I'm going to print the result. So probability that a car is sedan given it's a gas fuel type is, and I'll just mention this variable. So this is how we can solve the probability problems related to conditional probability. In this scenario, the
overall output that we see right now, the probability is 0.4378. So this is about the conditional probability. So I hope this gave you a quick revision related to the topic that we have seen earlier, that is the marginal probability, joint probability, and the conditional probability. You can also do your own analysis for this given data set for additional analysis and practice purpose. So with this, we come to the end of this video. As we progress in the next video, we'll look into an example of the application of Bayes theorem. So I'll see you in the next video. In this video, let's take up an example problem and solve it using Bayes theorem. So let's get started. Now here we've got a data set. Now this data is about the casino data. Okay, and I've got the various information about the probabilities. So first one over here, it says that the probability, okay, this is an interesting problem. The probability that a player is lying is given by 0.75. So this is actually a casino data. Okay, probability that a player is lying is 0.75, and probability that a player not lying is given by 0.25. Next, probability that a player win when he lied. So this is given by 0.43. Okay. Next, I also have one more data. The other data that I've got is probability that a player win when he did not lie. Okay, when he did not lie is given by 0.57. Now from this given data, I want to find probability that a player was lying, okay, given that he has won the game. So this is the overall problem that we want to solve. What is the probability that the player was lying given that he has won the game? So from this given data, we have the information that a player, what is the probability that the player is lying, what is the probability that he is not lying, probability that a player win when he lied, and probability that a player won when he did not lie. So here, okay, if I try to represent this given data, okay, I'm going to say that probability, if I call this as event A1, okay, is given by 0.75. That is probability that the player is lying is 0.75. And the probability that the player is not lying, I'll call it as A2, okay, this is equal to 0.25. Next, probability that, okay, a player win when he lied, okay, probability that the player wins when he lied, I'm going to say probability of B, A1, this is given by 0.43, and probability of B, A2 is given by 0.57. Okay, now in this example, I want to find what is the probability that the person is actually won the game. Here this is probability of winning given that he is lying, probability of winning given that he is not lying. These are the respective probabilities. Now I want to find what is the probability that the person was lying given that he actually won the game. So this is what I want to find. So let's go ahead and substitute over here and let's try to solve this problem right now, team. Okay, so here this problem can be solved with the help of conditional probability. So this problem can be solved with the help of conditional probability. So let's go ahead and solve the same as well with the help of our conditional probability. So here, in this example, so here we can actually solve it with the help of conditional probability. So if I want to find probability of occurrence of event A1 given event B is given by probability of occurrence of event B given A1 multiplied with probability of A1 divided by, yes, so probability of occurrence of event B given A1 multiplied with probability of A1 plus probability of occurrence of event B given A2 multiplied with probability of A2. Okay, so if I substitute in this formula, so this is actually 0.43 multiplied with 0.75 divided by 0.43 into 0.75 plus 0.57 multiplied with 0.25. So we get the values over here. We have from whatever the values that has been given to us. So we just substitute the values over here, and if we just substitute it, the overall simplified answer or the overall answer that we would get is 0.694. Okay, if we simplify this, this will be equal to 0.694, which is nothing but probability that a player was lying given that he has won the game is 69.4% or 69.4 probability. So this is actually 0.25. Okay, so this is what we have from this given data, and we are able to solve it with the help of Bayes' theorem of conditional probability. So the probability that a player was lying given that he won the game is 0.694. All right, team. So this was the quick recap on the concepts that you have learned about this Bayes theorem. So with this, we come to the end of this video. As we proceed in the next video, we are going to look into the hands-on data distribution. So we'll look into the various data distribution in a hands-on manner. So I look forward to seeing you in the next video. In this video, we are going to take up an example on data distribution and find the probability of occurrence of an event for a continuous value. So this will be an hands-on activity. So let's start by loading the data set, and I'll help you understand what is the expectation of this project, and then we are going to implement the same in a hands-on manner. So in this scenario, the data set that we are dealing with is called as students.csv file. Okay, this is a CSV file which contains the information about the students. So I'll start by loading this data set. So in order to do the same, let me just import the necessary libraries. Import pandas as pd, import numpy as np. So once I execute this, okay, next thing that I'll do is I'll start by loading this data as a data frame. pd.read_csv, here students.csv. So if I display first few entries, this is how the data set looks like. So we've got various attributes. We've got student ID, we've got name, gender, age, height, weight, religion, NC score, that is a score that he has scored in an examination, semester, major, minor, score 1, score 2. So these are the various values that we have got on this data set. Now, for the analysis purpose, I'm going to consider a single column, that is the height column. Okay, we are going to consider this single column, that is the height column. So what we will do is, for this column of height, we will check the distribution of the data set and check whether it follows the normal distribution or not. So we'll analyze the distribution of this column. We'll calculate the mean and standard deviation of this column of heights. And at the end, I'm interested in finding as what is the probability what is the probability that height of a student is greater than 175 centimeter and less than 190 centimeter. So this is the problem that I'm really interested to solve. I want to find the probability of occurrence of a student whose height is greater than 175 centimeter but less than 190 centimeter. So just think about it. What is the statistical value that I have to use? But before that, let's first look into the distribution of the data set. So in order to create the visualization, I'm just going to check df.describe. Okay, so if I call df.describe for the height column, so the minimum value is 135. That's great. And the maximum value that I've got right here, it is 206. And the average value is 171. So this is the overall information that I've got. Now I'll just get the histogram for this plot for this column of height. Okay, I'm going to create the histogram chart. So I would say df height dot hist. So this is going to create a histogram chart for me. Okay, this clearly looks like a normal distribution. Okay, we'll also check its skewness as well. So df height dot skew. So this will check whether the data is skewed or not. So we can clearly observe the skewness value is closer to 0, which means this data follows the normal distribution. And let's check the mean and standard deviation of this column. So the mean is, as we have seen earlier, it is 171, and standard deviation is actually 11.077. Okay, this is the standard deviation of the data. Okay, now what I'm going to do in this example is, we are interested in finding the probability that the height of a student is greater than 175 and less than 190, which means I have to find the values of Z1 and Z2, and using this Z1 and Z2, I have to ensure that I'm finding the value of CDF. So I'm going to calculate the Z1, okay, because we have to send in the Z1 score in order to get the probabilities. So I would say Z1 is equal to 175 minus mean. So what is the mean? This is the mean. Okay, I'll divide it by standard deviation. Okay, this is the value of my Z1, and the other value that I want to find is Z2. So this time it is 190, and I'll deduct from the mean. So once I have these values of Z1 and Z2, using these values, I'll take the difference of CDF of Z2 minus Z1. That will give me the overall probability. So P is equal to, I'm going to say, from SciPy dot stats. Okay, import Sci. I'm going to write it like this: import from SciPy import stats. So in order to find the CDF, I'm going to say stats dot norm dot CDF. Okay, so stats dot norm dot CDF, and here first thing that I have to mention is it's Z2 minus stats dot norm dot CDF of Z1. Okay, this will return the values of probability. So I'll print like this. Okay, the probability that height of student greater than 175 and less than 190 centimeter is, this is the P. So the probability score is 0.3255. Okay, so this is how we can apply the CDF for the data which follows the normal distribution. So if you remember in our previous topic when we did an hands-on exercise,
So we were actually dealing with the binomial distribution. Now this is a specific scenario where the data follows the normal distribution. When the data follows the normal distribution, we have to send in its z-score. We have to send in its z-score. Z-score is nothing but deducting the mean and dividing by standard deviation. We'll get the respective z-score to find the value of CDF. So in our example, okay, we wanted to have a specific range, hence we have taken the difference between 190 and 175, that is Z2 and Z1, CDF of Z2 and CDF of Z1. So in the end, we've got the values of probability. So with this, we come to the end of this video. Now, as we proceed in our next video, we are going to start a new unit, which is about the inferential statistics. So I'll see you in the next section.